Yep, it's on. Okay, welcome to Scientific Notation. Trinity Springs Middle School, 8th grade math. You don't know anything about scientific notation so far, but today you're going to learn a little bit by paying attention to me and Miss Walton in as quick as possible video that can still get you all the right information. So here's the introductory situation. We have a title, Scientific Notation, and then we have a bunch of non-examples right here, meaning they aren't scientific notation, and then a bunch of yes examples right here, meaning they are scientific notation. The problem is you don't know what scientific notation is yet, but if you use your brain and pay attention to the clues, you can figure out something about it by looking at the common qualities in the examples column. Here's what I mean. If I said just stare at these examples, maybe pause the video for a minute, and try to find some characteristics that all the examples have in common. Pause and think. Okay, now you're on pause. Here are the things I hope you found. In the example column, every example has multiplication happening in the middle. See that? Like all of them are multiplying. Over here in the non-example column, some of them multiply and some of them don't, but in the example, they all multiply. Another thing they all have in common is they have an exponent with a base of 10. Now the base just means it's the number at the bottom of the exponent. So all of these are being multiplied times 10 to some power. Over here, some yes, some no, not so much. There, every single one of them. Another thing they all have in common is they all have an exponent. It could be positive, it could be negative, but they all have an exponent. Good example. One more we're going to focus on over here. All of these numbers you may have noticed are positive. So I'm just going to put a little dot off to the side where a plus sign would be, and that means they're all positive. But there's one more thing that's really hard to spot, so I'm just going to write it out for you. The last thing that these guys all have in common is they begin with a number that is between 1 and 10. Meaning every single one of these numbers is between 1 and 10. So then if we look at the non-example category, we just try to figure out, well, what makes this not work? And on this one, there's just a gob of things like it's nowhere even close to the example column. This one, there's only one thing wrong with it. It's the fact that it's a 13.9, and we're only looking for numbers between 1 and 10. So that messes this one up. This number is too small. It's got to be between 1 and 10. This number's right, but over here, this is a little trick of the eyes. This one should have a 10 as a base. It doesn't. It has a 5, so that's what messes this one up. This one's just horrible. Like, who wants that much money anyhow? This one is too small. It needs to be between 1 and 10. And the last one, look at it. Look at it. What's wrong with that? Yep, it needs a multiplier, not an adder. So that's what messes that one up. Okay? So now I'm going to have you look at these and pause the video for a minute, and I want you to think through what you just saw about scientific notation and decide whether you think each one of these is an example of it or a non-example. Okay? Example or non-example. You're going to put a check mark if you think it's an example of scientific notation, and you're going to put a X if you think it's not. Wait a second. You're looking at a screen. You might just have to think about it. Better yet, I'll walk you through it. Forgot you didn't have this to write on. This one right here is a good example because it has a number between 1 and 10, a base of 10, and an exponent. This one is also a good example. This one is not an example because that 0.8 is not the right number. This one is not an example because that 8 is not the right number. This is not an example because it's just bleh. And then this one is good right here. And the bottom one is also not an example because this number right here needs to be between 1 and 10. Sound good? Super. That's how that rolls. Ms. Walton, tell us about baseball.
All right, so in baseball, if you're familiar, baseball, softball, if you have, I'll highlight the base right here. Oh. It could be a little interesting to see, okay, is this player that's sliding into base, is he safe or not? Is this guy's foot actually on the base? I don't know. So in a lot of sports, they do a lot of instant replays in order to figure out where it is. And in this case, we don't have an instant replay, but in scientific notation, our base is never going to move. So we're not going to have to worry about instant replays and to play through those things because our base is always going to stay the same and it is always going to be 10. Mr. Campbell mentioned the word base. So just like in baseball, we want our bases to stay in the same place. First, second, third, home base are going to stay in the same place. It's the same thing we have going in scientific notation. So this here is a prime example of proper scientific notation. We have a base of 10. We have some sort of exponent, which is that little number off to the side of our base, and we have a coefficient. So coefficient, we now have two definitions of coefficients, and don't let that confuse you. We're in a different unit. So our coefficient here is still being multiplied, but the key to this coefficient, like Mr. Campbell mentioned, is that it has to be greater than 1, and 4.1 is greater than 1, but it has to be less than 10. So we are in the clear with this coefficient, and we will move forward from there.
All right. Now we get to hit the Google Slides. So here we go. Google Slide. Present. This is a great example of scientific notation in that you have a number that's a big number, like that 40 million right there. Great number to have in your bank account. Maybe a bad number if you're like counting how many scratches you got from the thorn bush, but big number nonetheless. You probably won't have any trouble believing or buying into the idea that we can split that number into different pieces. Meaning, instead of 40 million, I could write 4 times 10 million. You know, if I had $40 million, I could put it in 4 different bags with $10 million each and carry it around. I would still have the $40 million. But if you remember from last week, we saw that when you have a number 1 with a bunch of zeros around it, that can be rewritten as a power of 10, meaning 10 million is 1 with 7 zeros, and that means it's the same as 10 to the 7th power. So if I split my 40 million into 4 times 10 million, I can also split it into 4 times 10 to the 7th power. That is the same as that, which is the same as that. Now skip that video and then look at this as another example. We have another big number up here that is 3,400,000,000, or as a politician might say if he was spending your money, just 3.4 billion. Not a big deal. If you wanted to break that up into 2 pieces, you'd break it up like this. The first part, we would find a number between 1 and 10, 3.4, and then we would multiply it by this big number over here, which is a billion, and so it'd be 3.4 times a billion, which is 3.4 times 10 to the 9th. And I'm guessing some of you guys are wondering, where did we get this number from, and where do we get this number from? So here's where we got it from. Shifting sides. When you see your really big number that you want to turn into scientific notation, you are going to take the original place where the decimal was right here, and you're going to move it. You're going to move it through the number until you put it in a place where you make a new number between 1 and 10. Watch. Decimal used to be here at the end of the number. 1, 2, 3, 4, 5, 6, 7, 8, 9. I moved it 9 spots, and now I'm sitting right here at 3.4. I've made a new number, kind of, right? And that new number is going to be the coefficient of my scientific notation. That's how I got 3.4. Looking for a number between 1 and 10, yada, yada, yada. Then the second number you figure out by asking yourself, how far did I move the decimal? And I moved the decimal 9 spots, so this second number is going to be 10 to the 9th power. If I'd moved it 12 spots, it would have been 10 to the 12th power, and so on and so forth. So 10 to the 9th, 1 followed by 9 zeros, that's a billion. 3.4 times a billion is 3.4 billion. Likewise with this one, 761 million. Decimal used to be here. Now we need to find a new number, be able to make a new number that we can draw out of it, and that new number needs to be between 1 and 10. So 1, 2, 3, 4, 5, 6, 7, 8. 8 spots over. New number is 7.61 times 10 to the 8, which is 100 million. Last one, you'll never see one this complicated when you're doing stuff in class. I just wanted to show it to you to help alleviate a possible problem. Here's the possible problem. A lot of folks sometimes get locked in the mindset that they're counting how many zeros there are. You don't have to count the zeros in the original number. It doesn't matter how many zeros there are. It matters how far the decimal moves. Keep that in your head. Because if you just counted the zeros, you would have come up with 10 to the 6th. But that's not the right answer. It's 10 to the 8th because the decimal moved 8 spots. On this big number, decimal was here, moves all the way over there, and then you get a really weird, wacky number that says 1.2978164, and then I kind of rounded the rest of it, times 1 with 10 zeros after it, which is 10 to the 10th power, which is 10 billion, which is a nice big number. Don't need that video. So exit all that out and hand it over to Miss Walton for stage next. There you go.
All right, so you will have the option of printing this if you so choose, or maybe just showing your work on a separate sheet of paper. This PDF will be available online on Google Classroom. So in math, there are sometimes ridiculous things, and you're like, for example, Sally bought 30 million watermelons and Harry bought 30 million watermelons. And you're like, why are they buying so many watermelons and who sells that many watermelons? So sometimes we do, like, the word problems in math are sometimes a little crazy. So just bear with us as we go through this example of measuring the length of a football field in inches. And you're like, we already know that a football field is 100 yards. Why would we need to measure it in inches? But for those of you that are in football, you can tell your coaches, did you know that a football field is this many inches? And they'll be impressed. So for mere impression purposes, here we go. So Mr. Campbell helped us break down the different requirements for scientific notation. And we have a really nice scientific notation here, 3.6 times 10 to the third power. And so this is written in scientific notation, and they're asking us to convert it to standard notation. And that is just a fancy way of saying make it a normal number. Standard notation is just a normal number. So this number, 3.6 times 10 to the third, looks a little scary, and so we're just going to turn that into a normal number. And we're going to do that by looking at two key indicators of this scientific notation. We're going to take the coefficient, which is 3.6. I'm going to go ahead and write that 3.6 here. And then I'm going to find my exponent, because my exponent is going to tell me how many places I'm going to move my decimal place in the positive or negative direction. So in this case, we have 10 to the third. And so that means we are going to move our decimal 3 places in the right direction. So I'm going to take my decimal here, move it 1, 2, 3. So I'm going to make my new decimal point really big so I can see it. And then in these little divots here, I'm going to add other zeros. So our final answer is a football field is 3,600 inches. And if you tell Coach Toller or Coach Eschlinger or Coach Wallace, they will be so impressed with you that a football field is 3,600 inches. They probably don't even know that. All right, so another thing, maybe if you're sitting at home, you can, if your hair's long enough, I don't think Mr. Campbell could do this, but if you pull a hair out and you're able to look at it and you're like, I wonder how long that is in meters. And then they told you in scientific notation that the width of a human hair is 6 times 10 to the negative 5th power. And you think, wow, that is a really, really small number, but why are they measuring it in meters? Again, sometimes in math, they just do crazy things to show a point, I guess. So we're going to take our coefficient. So this one was 3.6, but now we have a 6. So the problem is here, this one we knew to move the decimal because it was right in between. But sometimes we don't have a decimal shown, so we know we have this imaginary decimal after our 6 in this location here. So since we have a negative number, a negative exponent, we're going to be creating, moving our decimal to the left. So I'm going to go ahead and move it left 5 times. 1, 2, 3, 4, 5. My new decimal place is going to be here. And in each of these little divots, I'm going to add a 0. 1, 2, 3, 4. So our new number is 0.00006 meters. And when you go get your haircut next time, you can tell your barber, haircut person that, did you know that the width of a human hair is this many meters? And they will be so impressed.
Measure by the meters. But Miss Walton, how did we know that that was going to be such a small number? Like, why are some exponents negative and other ones positive?
Well, Mr. Campbell, thank you for your question.
Oh, you're welcome.
When we have, if you think we know by seeing things, right, that a football field is really, really big.
Oh, yeah. It's
and
bigger
then
than my hair.
It's bigger than a width of your hair, right? So I have one last thing to show on this slide. So we have 2 blanks to fill in, and I'm going to help you real quick. So a positive exponent, if we make a T, it kind of looks like a positive sign addition. So positive exponents will result in a really large number, okay? So if we look here, larger number, this 3.6 with a positive exponent became a larger number. Whereas when we have negative exponent, we're going to create smaller numbers like this. So we have smaller. And if we know the width of a human hair, we went from 6 to 0.0006, which is a lot smaller, and that is the indication of positive and negative exponents.
Thank you so much, Miss Walton. Now it's all clear. Now, what else? More down the notes. Speed of light, converting from a standard number, a really big number, to scientific. I look at that, I go, well, right now the decimal's right here. I'm going to bump it over 1, 2, 3, 4, 5, 6, 7, 8. My new number is 3 times 10 to the something. 10 to the what? 10 to the 8, because that's how many decimals I moved it. It's beautiful. It works great. Uh-oh. Now we have one of them tiny numbers. The mass of a dust particle in kilograms. Yikes. Well, I'm still going to do the same thing. Find where my decimal is, then move it where I want to be. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now I have a new number between 1 and 10. It's 7.5 times 10 to the, I moved it 10 spots, but is that a really small number or a really big number? That's a really small number, which means my scientific notation is going to be to the negative 10th, not the positive 10th. Don't forget that. Rules for scientific notation. Miss Walton, I'm not very good at rules. Would you come talk about this?
All right, so we have a couple of things underlined, and I'm going to underline a few more things. And again, this isn't going away. You'll be able to read over this in your notes yourself. So I'm just going to take a few moments to highlight some things as to what makes scientific notation and why and what qualifies a number to be scientific notation. So the first thing is that there are 3 parts in scientific notation. We have coefficient, a base, and an exponent. And we talked about, just like in baseball, we don't want that base to move. So in scientific notation, that base is always going to be a 10. Just like all of my students, you are a 10. 10 out of 10. And the coefficient, I skipped over this one, has to be between 1 and 10. So
10.
1 and 10. And then
there's some more information right there. And pay attention to it. It's the rules.
it's the rules. We don't
Next.
make the rules. We just follow them.
We follow them. Math makes the rules. So write each of these in standard. I'm going to do the first one, and then I'm going to let you do the rest on your own. And then I'm going to go to the last part and do the first one of those. So you see this, you go, well, I've got my basic number, which is 3.9. I need to move it 10 to the negative 3, so I'm going to make a smaller number. So I go 1, 2, 3. These little gaps right here, you fill in with zeros, okay? Because you moved a decimal over here. And so you put a 0 here and a 0 here, which means your new number is 0.0039. So boom, boom, boom. Fill in the trenches with zeros and you're good. You do the rest of them. And then on the last part of the notes, Write the following numbers in scientific, going the other direction. Start with a 1,200,000. Decimals here. Bump it 1, 2, 3, 4, 5, 6 to make our new number. Our new number is 1.2. It moved 6 spots. It was a big number, so it's going to be a positive exponent, and the answer is 1.2 times 10 to the 6th. I'm going to show one more just in case. When you see a big number that has multiple whole numbers as part of it, like this 235, 2,350,000,000, then I don't want you to make a mistake and get confused on where to put the decimal. You still take it all the way to a point where you make a number between 1 and 10. So 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12 spots right there. And here's what some people do that's wrong. They go, oh, our new number is 2.3. No, it's not. No, it's not. Look, there's another number there. It's 2.35. You got to keep it all. Don't just throw numbers away. They might represent money. So it's 2.35 times 10 to the, I think we moved to 12 spots, so 10 to the 12. That is how you land that plane. There's going to be practice coming up this week. There's the rest of these notes. You're going to practice on those. There is going to be some stuff pop up on Google Classroom tomorrow that we're doing. And then we're going to have an IXL lesson and a quizzes at the end of the week, either on Thursday or Friday, that you're going to be looking for. So you'll need this to do that well. Sayonara.